How are you doing? Are you ready to dive into the practical aspects of hardware hacking, that is, software and hardware hacking? And yes, as was correctly mentioned today, we will not only talk about the theoretical foundations, but we will also physically hack a radio-controlled doorbell together. It whistles a bit. Yes, it's a little loud, but we'll go through it together. Today, of course, we're talking about SDR. So a question for the audience. Who here has ever heard of it and knows what it is? Wow, a forest of hands. May I ask you? Yes.
It's software-defined radio.
Yes, that's absolutely right. It's software-defined radio. That is, when Popov invented the radio 150 years ago, analog tools were used. So that's an inductor coil, capacitors, what we call a resonant circuit, and of course the antenna and grounding. And in this way, radio waves were either generated or received. At present, just like in any other equipment, analog tubes have been replaced by transistors. And in radio equipment as well, physical devices have essentially been replaced by ordinary transistors and, in fact, by software-based solutions. Well, in polite society, it's customary to introduce oneself and say hello. So let me introduce myself once again. My name is Ivan Glinkin, and I am an expert in the field of information security with over 20 years of experience. In brief, I have 2 higher education degrees, 10 certifications, and 3 CVEs. You have probably heard of institutions such as MIT, Harvard, Stewart, Stanford, Cambridge. I've hacked all of them, including Stanford, where I received 2 RCAs, one of which was under the mouth. And of course, everyone has probably heard of Hack the Box too, right? I didn't hack their machines, but rather hack the box itself, for which I also received corresponding letters of recommendation. And finally, a bit more about myself. In about 2 months, my book will be released, which is also about software-defined radio, covering a similar topic. So I also recommend checking it out. What are we going to talk about today? Well, the first 20 minutes will naturally be about the theoretical basics. So I'll try to make it interesting so you don't fall asleep. And for the remaining 20 minutes, as I already mentioned, we will hack our radio doorbell in several different ways. Well, and let's go. I actually have a question for the audience. What is a radio wave? Who knows? Who can answer? That's right, yes. It's electromagnetic radiation that operates within a certain frequency range. According to the standard classification of the International Telecommunication Union, it's basically from 3 kilohertz to 3 terahertz, which is quite a wide range, a pretty broad spectrum. In fact, the wavelength can range from a few millimeters to even several kilometers. Can you imagine a wavelength of, say, 10 kilometers at a frequency of 3, kilohertz? Question. Basically, it's a pretty easy one, and even those who have never dealt with this can actually answer. What properties do you think radio waves have? Could you speak up? I can't hear you. What?
Wavelength and frequency.
Wavelength, frequency, but specifically physical properties. What can it do? Permeability? Yes, that's penetration. There's also reflectivity, right? Remember from physics, the angle of incidence equals the angle of reflection. A wave can also bend around devices, bend around obstacles if we're talking about houses, trees, or any other physical barriers. Maybe you've heard, by the way, that about 5 years ago, researchers created so-called devices for basically seeing through walls using radio waves, specifically through Wi-Fi. Because waves, as you correctly mentioned, have the property of penetrating through objects, and accordingly, by analyzing the reflected signals, it was possible to reconstruct the image. Yes, I apologize for any technical issues that may have occurred. Oh, there we go. And actually, I've already answered the third question, yes. So what are the frequency ranges of radio waves? And as I already mentioned, it's from 3 kilohertz up to basically 3 terahertz. And as the young man from the first hall correctly answered, it's electromagnetic radiation. And in addition to radio waves, there are also, of course, visible waves as well as invisible ones, including ultraviolet. Things that can be seen, things that can be heard, and also gamma, alpha, and beta radiation, that is, even X-rays. And to demonstrate this visually, because we can't actually see or hear a wave itself, but if we use an example, actually everyone has seen them. What do they look like? Basically, it's a sine wave. And here, a number of characteristics that waves possess are also shown. And one of them is, again, interference. We forgot to mention it on the previous slide. This is when one wave overlaps with another, and well, our signal disappears, we lose it. And by the same principle, basically, it's similar to white noise. That is, when we turn on some device, it drowns out everything, or rather, it doesn't exactly drown out, but it emits radio frequencies of a certain amplitude and wavelength into the air, and in fact, due to the signal's power, it suppresses the other waves. So the main signal doesn't disappear anywhere, it's just that the source of the radio channel is so powerful that it suppresses it. And in this way, in fact, we can see interference in a real-life example. So radio waves can be emitted in various ways. Yes, basically, if we're talking about the payload, about the radio wave signal, we have a carrier channel, right? The carrier frequency can be either analog or, of course, digital. We can also have the actual data that we transmit, which in turn can also be divided into analog and digital. And accordingly, we also have modulations that are actually used to transmit the useful signal on the carrier frequency. Here I have AM and FM modulations shown. That is, AM is amplitude modulation, FM is phase modulation. And as we can see, the carrier frequency is a uniform radio wave of a certain frequency and a certain amplitude. And we have the useful payload that we want to transmit. And depending on the type of modulation we use to transmit the radio channel, the final radio wave that goes on air can take different forms. In this case, we have amplitude modulation that is along the height, along the y-axis, if we speak in strictly mathematical terms. So it is superimposed and the carrier frequency changes. Or we are talking about frequency modulation, when the frequency of the wave itself changes, but the amplitude remains at the same level. So in principle, we can transmit the same signal on the same frequency, the same channel in up to 11 different ways. Which one to use is, again, up to you. Some are more susceptible to interference, some are less susceptible to interference. And again, the choice of a particular modulation or frequency, which refers to the specific way in which signals are transmitted or received, depends entirely on you as the user and is determined directly by the specific conditions and requirements present in the environment in which it is used. These conditions can include factors such as interference, distance, and the type of communication needed. Next, let's talk about wavelength. Before that, I will ask a question. Why do you think we, as researchers, as specialists in software and hardware, need to know why the wavelength is needed? What is it? That's right. The main reason we need this is to select the appropriate antenna. There are different types of antennas, and we'll talk about them a bit later. But before that, yes, let me bore you a little more with some theoretical aspects, specifically how to actually calculate the wavelength. It's simply dividing the speed of light, which is about roughly 300,000 meters per second, by the frequency, and essentially the wavelength is inversely proportional to the signal frequency. Let's take a look in practice at what the wavelength will be for different frequencies. For example, let's take the regular FM band, the radio frequency band. So when you're driving in your car and listening to the radio, for example, the frequency might be 100 megahertz. To calculate its wavelength, we simply divide 300 million by 100 million. Why 100 million? Because a megahertz is, accordingly, mega means 10 to the 6th power. And we get that the wavelength for regular radio, the kind we listen to in the car, is approximately 3 meters. If we're talking about IoT devices, smart homes, and including the doorbell we'll be using, they operate at a frequency of 433.92 megahertz. This is, in principle, a universal international frequency that is used anywhere in the world, specifically for IoT devices. The formula is similar. 300 million divided directly by the frequency, in this case 433,920,000, and we get that the wavelength in this case will be just under 70 centimeters. And accordingly, the most common one that everyone encounters in their daily life, sometimes several times a day, is of course Wi-Fi, which operates at a frequency of 2.4 gigahertz. Using the same formula, you can see that the wavelength is only 12.5 centimeters. As the young man in the second row correctly pointed out, we need the wavelength to assess and calculate the antenna, because a strong and clear signal is necessary for us, once again, to carry out a proper attack. It's not just about receiving the signal, but also about transmitting it. This is especially true if we're talking specifically about either a replay attack or an attack by synthesizing the signal and so on. Well, I think basically from your introductory physics course, you all remember what this is. That is, the distance between the wave peaks is its frequency. Amplitude is, in fact, the distance from the peak to the trough, from the trough. And essentially, frequency is the number of peaks per second in terms of time. We have different types of antennas. And as you can see in the FM band, the wavelength is 3 meters, but on no cars, or in fact on any home devices, have we ever seen a 3-meter antenna. And that's why to receive and transmit signals at, for example, this frequency, so-called half-wave or quarter-wave antennas are used. That is when we divide the wavelength in half or into 4 parts. Well, in this case, if we're talking about the FM band, then half a wavelength is 1.5 meters. So you could use a 1.5 meter antenna. Or if you divide it by 4, 75 centimeters. Sometimes antennas are designed in very interesting ways to reduce their height. So probably on the next slide, I'll show you. Let's move on to this. In this case, as you can see on the flipper 0, remember that the wavelength for IoT is 69 centimeters. But here, the antenna is made in the form of a spiral. So it's the same 60, but here it's a half wave, meaning 30 centimeters. But how can you fit 30 centimeters into such a small device? They simply coiled the antenna and basically used this technique. Let's talk accordingly. Let's start gradually moving on to practice and discuss the equipment we use for SDR. For some of you, these images might already be familiar, but let's talk about the basics. RTL SDR is a really cool thing. It was developed literally no more than 10 years ago. Essentially, the device is just a regular microchip taken from a television receiver. Then they added some circuitry and so on. And in fact, you can still buy it today. It is used for our purposes. There are 2 main drawbacks. The first is a somewhat limited frequency range in which it operates, only up to 1.6 gigahertz, meaning it doesn't cover Wi-Fi or Bluetooth. And also, this device cannot transmit a signal into, well, the airwaves. In other words, it can only receive. Moving on. The much talked about and widely known Flipper 0 also has the capability to receive and transmit radio signals. To be honest, I'm not really a fan of it, for 2 simple reasons. The first, of course, is the unjustifiably high price. Secondly, once again, it has a limited frequency range, only from 300 megahertz to 900 megahertz. So it covers mainly IoT devices, including various types of smart devices and a bit of GSM technology, but that's basically all there is to it. And again, there are inconveniences in using it, as well as the need for additional software, again, through a computer. Next. No, that's not necessary. Moving on. Lime SDR is a very expensive, high-quality device. Many professionals use it, yes. The main drawback, of course, is the price. It costs an outrageous amount of money. In some cases, it's even impossible to get one. But its main feature, aside from the range of received and transmitted frequencies, is that it can operate simultaneously in both receive and transmit modes. For example, if we take the Flipper Zero or the HackRF, these are half-duplex devices, meaning they can either receive or transmit at any given moment, but not both at the same time. Meanwhile, the Lime SDR can do this simultaneously. Why is this necessary? Well, aside from hacking GSM, the well-known mobile signal, this feature isn't really used anywhere else for now. Again, the Blight SDR can also both receive and transmit at the same time. HackRF, it's also displayed here on my stand, and we'll be using it to carry out all our current demonstrations. HackRF was developed around 2014 by Michael Osman, who founded his company Great Scott Gadgets. What's good about it? Aside from the high price of the original, Michael Osman made it open source, so anyone interested, including our colleagues from East Asia, let's put it that way, learned how to make it themselves. And now, for example, you can buy it on the well-known Chinese marketplace for no more than 10,000 rubles. All of this is legal, it's all legitimate, and it complies with all our regulatory documents. The main requirement for radio devices manufactured in the Russian Federation is that the transmitter power must not exceed a certain threshold. In this case, it's half a watt, and unfortunately, the signal transmission range is limited to 50 meters. But for research purposes, that's more than enough. And if you actually want to have some fun and play around with the law, then of course you can install additional amplifiers, amplitude boosters, and so on. Next. AirSpy is also a miniature device for receiving and transmitting. This interesting little thing here is directly from either a Raspberry Pi or Arduino kit, which allows you to receive and transmit, well, separately transmit and receive signals separately, but only on a single frequency. 433.92 megahertz, which is specifically for IoT and smart devices. As you can see from the crystal, this one will be the transmitter, and this device will serve as the receiver. A major drawback, so to speak, of using it is the need to purchase additional peripheral equipment, meaning either a Raspberry Pi, or what else do we have? Arduino, or other boards. Basically, you need the boards, set up the circuitry, and write the code yourself. So, if you're an enthusiast in this area, yes, you'll get a lot of enjoyment working with these devices. And currently, the best, more or less, let's say, affordable device for the average person to work with software-defined radio waves is the USRP. A brief comparative overview, I think it would be interesting to take a photo of it, yes, to understand which device is actually more suitable for whom. Here, I tried to specify as accurately as possible the minimum and maximum frequencies at which these devices can operate. So, as you can see, the HackRF, which is presented at the stand, operates at frequencies from 1 megahertz to 6 gigahertz. Again, this refers to the channel bandwidth. In other words, it's about what bandwidth the device can simultaneously process. By the way, this is important for analyzing the radio environment around you, including within your company. When we were actually engaged in protecting information from leaks through technical communication channels, we were accordingly searching for all sorts of bugs and transmitters, devices that could be planted, for example, in the offices of company executives or, say, in research departments and divisions, which can actually be stolen, yes, and in fact used to gain some kind of financial benefit. And it turns out that the device scans the radio channel in segments, not all at once from 1 megahertz to 6 gigahertz, but in parts. For example, if we're talking about the HackRF, by 20 megahertz at a time. For the device to cover its entire channel width, its whole range in steps of 20 megahertz, well, it would take about 2 or 3 seconds. In principle, you might say that this isn't all that much, we can tolerate it, but sometimes signals can pass by in literally fractions of a second, and you won't have time to catch them. Either you'll only catch the initial part, or you might only catch the final part. And then after that, you already need to tune in. And in fact, yes, the resolution of the ADC. The next question is, can it transmit or not? Which is exactly what I was talking about on the previous slide. As you can see, yes, only ASPA, SDR, and RTL SDR cannot transmit. everything else in principle can work both for receiving and transmitting, well, I think, yes, ordinary people will also be interested in the last column. Yes, how much it costs, how much you need to spend to get started with this. That's why, in principle, this field isn't for everyone, because there's a high entry barrier, not only in terms of knowledge, but also in terms of financial investment. Here I've indicated that the HackRF, which is a software-defined radio device popular among hobbyists and professionals, costs $300. However, it's important to note that this is, let's say, the price specifically for the original unmodified product, as it is officially sold on the official website of Michael's Code Company, which is the company founded by Michael Osman, the creator of HackRF. But, as I mentioned earlier, clones, basically copies made by our colleagues abroad, can actually, in fact, be purchased for even less than $100. The next question we need to address before we move on directly to the practical part is to talk about the software that is used. There's a lot of it, more than 30, 40, even 50 different applications that work with various devices. Some are universal, like, for example, SDR cubes or GQRX. Others are specialized for specific devices. But in this case, I will also be showing you in practice the console version of working with the HackRF 1. So if you prefer, once again, to use the console to type commands, and again, why is the console often so disliked by us? Really? Because we can create various types of redirections, set up additional wrappers, and of course configure the system ourselves to work for our own specific needs and requirements. We have a lot of flexibility. This means we can adapt the setup to suit different situations or preferences, making it highly customizable. So with all that in mind, let's move directly to the practical part of this process. As mentioned earlier, we are now going to hack this radio-controlled doorbell, which means we will modify its internal workings to change how it operates and interacts with other devices. So we press the button, you can hear that someone has arrived, right? Please open the door. In fact, this is just shown as an example because the same principle is used for your sliding gates, barrier opening, car alarm, and anything else you can think of. Basically, everything works according to the same principle, following the same example. But in this case, again, for the proof of concept, for now we will use a regular doorbell. Before we usually hack radio waves, as my colleagues, the previous speakers, have reported, it is, of course, preferable to take it apart and see how it works. Well, in this case, there's nothing complicated. A power source, a battery, a button, a generator for the carrier frequency, the microchip itself where the payload is generated, and 3 transistors for amplification. There is an antenna present here as well. Unfortunately, it's on the other side, and it's made on the printed circuit board. It's simply etched onto it. That's exactly why this particular transmitter actually looks like this on the inside, with all of its components visible. So let's go ahead and carefully hack it together. We'll hack it in several ways. First, we'll carry out a standard replay attack using the native software for the HackRF, and then we'll perform a similar attack in the GUI version, that is the visualized one, right? And at the very, very, very end, we'll carefully and methodically break down and thoroughly analyze the signal, and and then after that, we'll synthesize it. Let's switch to the command line. So it looks like the HackRF is connected. Let's check HackRF info. As you can see, yes, the HackRF is connected. Sorry, can everyone see clearly, or should I make it even bigger? Is it good for those in the back rows? Everything's great. Accordingly, the serial number, firmware date, and yes, it shows here that mine is a little outdated, but in this case, if it works, don't touch it. We don't need any extra features for now, so we can put up with it. So the next program we'll be using is, in fact, HackRF transfer. So what are we doing here? All right, let me do it like this so it's easier to see. What are we doing here? Naturally, with HackRF transfer, we launch the program itself. It has many keys. One of them is, again, FF. As you can guess, actually from the next number, is the frequency. The frequency is specified in hertz, so you need to include everything right down to the last 4 zeros. Well, in this case, as you can see, it's 433,920,000. The next flag we use is the S flag. This is our sample rate, that is the bandwidth. Roughly speaking, It's how many symbols we will capture per second with our device. And the R flag simply tells us what to name the file where we will save the captured signal. So what do I do next? As I mentioned, we have the hack RF, we have the antenna connected, and we have the transmitter itself. Now I'm going to press the enter button again. Our program for receiving the signal will start working, and at the same time I will press the transmitter, and our channel, which is going, our signal, which is going from the transmitter to the buttons before the bell, it will be recorded for us. I press the enter button. I press record, and basically I close it. In theory, as I think, if everything went well, because sometimes we have various issues with technology, our signal, someone is probably messing around with a flipper 0, right? Well, please don't do that. But the idea is cool, yeah. Later you'll tell me what code you have there. 66, there should be something, and we'll decode it together. Yeah, but that's for later. As you can see, our channel, the signal, has been recorded, and now we're going to carry out the most classic script kiddie attack, the one you basically saw, just like the young man in the front row demonstrated. We're going to perform a replay attack. That is, we won't bother figuring out what's inside, what kind of payload is there, or what code is used. We simply take the signal we've recorded and send it back out over the air. For this, we'll basically leave everything as it is. We'll leave everything as, oh, wait, I see. You can't see it, right? Let's do it like this. We leave everything as it is, except instead of R, we'll specify the T key, meaning transfer, to send which file, as you remember, was recorded as a, and -47 indicates the power level with which we'll transmit this signal. Because by default, the power is very low, and even at this distance, the call itself won't receive the signal, since the transmitted signal will be too weak. In this case, we're explicitly specifying HackRF, that we want it at maximum power. Everything you've got, put it all on the air. Well, since you're the most active one here, why don't you hold the call for us, so everyone can see that I didn't press it? And basically, we'll transmit it wirelessly over the airwaves. You're not pressing it, as you can see, right? So no magic here, right? Just sleight of hand, no trickery. So in this case, we've just carried out a simple attack. Once again, this is called a replay attack. That is, we simply recorded the signal and sent it back into the air. We didn't analyze what was inside it. The next program I want to show you, which we'll use to carry out the same attack and then analyze the signal, is Universal Radio Hacker. I assume that those of you who are more or less familiar with this topic have probably heard of this program. It's a super powerful application. I really love it. And I actually recommend you start with it if you decide to get into hardware hacking. For this, we'll record a new signal. Could I ask you to return the prop? What are we doing here? Actually, the program's interface is very simple. The first thing we need to do is select the device we'll be using for this. As you can see, the list is quite extensive. So regardless of what you buy, HackRF, RSP, Lime, and so on, basically all of these are supported. So once again, it's entirely up to you. Choose whatever you prefer, depending on your budget. The frequency here is set by default to the standard IoT device frequency, which is 433.92 megahertz. And for the sample rate, let's also repeat what we did in the previous step, namely 2 megahertz. Basically, the situation is the same. We click the start button, that is to start recording. At the same time, I press the doorbell, we intercept the signal, and then we take a look. Well, I think that should be enough for us. As you can see, we've recorded the signal. Let's save it somewhere, say on the desktop. It's appeared there. Let's close this. And now let's take a look. I suggest we delete the unnecessary parts, just like this. The program's functionality allows us to do this and take a closer look at the payload. Yes, at the actual useful data that was sent. A question for the audience. What interesting things do you notice here? Yes, that's absolutely right. I'll repeat what the young man in the front row said. As you can see, the signal we're transmitting over the air is always the same. In other words, it's a fixed code. No matter how many times we press the transmitter button, the same code, the same payload will always be sent. This is essentially the principle behind attacks such as replay attacks. That is, we record the signal without analyzing or understanding it, and then simply send it back. If this particular device used what is called a rolling code or a dynamic code, then each time the button was pressed, a different payload would be generated. And for us, as information security specialists and experts, the next task would be to find the algorithm, to find the formula by which the transmitter generates a particular frequency, generates a particular signal, and the receiver recognizes it as legitimate and then processes it accordingly. It is precisely according to this principle, the rolling code principle, where the payload changes every time that, among other things, car alarm systems operate. If we're talking about very expensive, let's say, sliding gates at certain places, including government facilities, it's the same thing. Why do I also like this program? As you can see, it has a built-in automatic decoder, and it immediately breaks down the signal for us in digital form, showing where there is a 1 and where there is a 0. The next step we want to take before actually playing it back is to demodulate it. In this case, as you can see, by default, it is set here, and in the lock as well, basically, yes, it uses ISK modulation, amplification key. It's the same as AM, except instead of, roughly speaking, a floating sine wave, we transmit ones and essentially zeros. And again, this application is really great, and it can demodulate it. And look at what we got after we clicked on demodulation. As you can see, it's a beautiful code. Zeros and ones, basically just like our entire IT infrastructure is built on. So accordingly, we won't close this for now, because we'll definitely need it later on. So let's go ahead and carry out the attack. Let's do a replay attack in reverse. That is, we just press play again, and so as you can see, I didn't set the signal power. Here it is, that's the gain. And that's why, even though the antenna is right next to the receiver, nothing happened. I'm holding the button, not pressing it accordingly. And now, as you can see, we've basically done the same thing together. I just went silent for a moment. We've done the same thing. Yes. Now a woman with a microphone will come up to you and you can ask your question.
Could the signal be analog instead of digital?
How? Analog?
Yes.
Well, basically, an analog signal, to give a simple example, is like radio, because it doesn't jump sharply up or down. But in this case, I think it's unlikely, because then the manufacturer would have to make significant changes and invest a lot of resources to actually make it happen. But usually, when we're talking about digital things, a digital signal is used after all. But essentially, it's analogous. Only instead of sine waves, everything is just parallel and perpendicular.
Well, if I'm not mistaken, this is digital, right?
Yes, it's digital.
Thank you.
So the analog is implemented in digital form. All right, it looks like we've already figured out what the signal looks like, haven't we? And the next thing we're going to do, where's our presentation? Yes, right now we're going to make a radio-controlled remote. Go ahead and take a picture of it. I assume that would be interesting. Yes, take a picture. Who knows what this application is? Well, no, huh? GNU Radio Company. Yes, that's correct. Let's go ahead and open it up again once more. All right. Just a moment. GNU Radio. GNU Radio Company. To save time and not bore you too much with theory, I already have everything preloaded. Let me make it bigger. I don't remember how to do it here. There we go. This is a professional level schematic. In other words, this is, let's say, a transmitter at its maximum potential. And we also have a basic, let's say, simple schematic, the one you just saw on the slides. So what is GNU radio? GNU radio is basically like Lego. It's a programming language similar to Scratch. So what is it exactly? Basically, you can simply choose from the available blocks that currently exist, well, at least the ones that are presented here on the screen, and then drag them around as you like. No, any of them, whichever you want. Connect them together. And after you click the play button, this code will, in a straightforward and automatic manner, be rewritten as a Python script, and you can very easily run it later on, even without opening GNU Radio Companion at all. So essentially, it's just a visual compiler into a Python script, kind of like a basic version of ChatGPT. What do we have here? In order to synthesize a signal, not just do it like in ScriptKit, where you record, send, and so on, but in order to, if we have rolling and so on, you could again use Python to create an algorithm that would constantly send something different, not just the same thing. But in this case, since the example is quite simple, we just need to send a constant signal again. It looks pretty scary, like this. Why does it look like this? Because we are transmitting ones and zeros in the exact form in which we got them from the previous example from Universal Radio Hacker. That is 1, 3 zeros, 1, 1, 0, and so on. Where is it here? Here it is. Just a second. Let's highlight it somehow. Here it is. 1, 3 zeros, 1, 1, 1, and so on. Actually, for a computer, it's... Well, obviously, computers are quite powerful nowadays, and tweaking 100 samples or 25 isn't that big of a difference. But if we're talking about radio, then again, this becomes very critical. Next, we have repetition, the so-called repeat interpolation. In this case, we're showing how wide this one should be. Because as we discussed earlier, yes, the wavelength, the distance between peaks, and so on, are all different for each. In this case, it's extremely critical. We're indicating how much time, yes, how many units a 1 should correspond to, how much time a 0 should correspond to, and so on. Next, we multiply all of this by 0. Why? Because we have a button. Here it is, the GNL push button. And basically, when we run the code, a window will open. Well, as usual, we imagine where a regular button will be, the one will press. And essentially, the signal is modulated, synthesized. And basically, we send all of this to the HackRF sync. That is, this is where our generated signal is actually sent. In this case, it's our HackRF. Here, we've already preset the frequency to 433 megahertz and the sample rate. Let's run it. And we get this beautiful image. Again, I'm not touching the button, just holding the antenna, preferably close by, yes. And after I press the button to ring the bell again, it should start playing. So in this case, we didn't just perform a simple replay attack. We actually synthesized the signal. In other words, we created it from scratch. If we're talking about more professional circuits, it's this one. I recommend taking a photo of it. Everything here is pretty clear, right? I recommend taking a photo of it. But here, our vector source is presented in a different way. Not those thousands or hundreds of ones, but like this. What do you think? Why is that? Yeah, it's tough.
Is this just the data? And the rest of it is...
No, this is data, this is data.
32 bits, or how many is it?
Again, this relates to your question. Well, what I was asking, why did your flipper 0 capture the signal not as 010, but as 66 and so on? Because it converted it from the physical state, from the actual tangible physical state, into what we call logic or logical form. So in this case, for example, let's imagine that a short pulse and a long pause represent a 0, and a long pulse and a short pause represent a 1. So we move from physics to logic, and in this case, it would look like this. 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, and so on. Right? No, that's something else entirely. Let's discuss it after this, once we've finished here. In this case, in this particular situation, we've simply converted the exact same physics into logic, step by step. And again, if we take the resulting code, where is it here? Yes, here it is, and convert it. Damn, there are a lot of these commas. Actually, let's go ahead and do it, since we still have some time left to work with. If we now go ahead and edit the code, for example, if we replace or delete the commas, or if we use the replace all function to change every instance at once, we can see the effect. If we take this code, specifically the section labeled BC, and if we translate this code, let's do it like this, placing the translated version somewhere here for comparison. This way, we can clearly observe the changes and understand the impact of each modification. If we convert it from binary to hexadecimal, we'll get, as you can check, the equivalence. Similarly, yes. The only difference is that we removed the leading 0, 0, 1, but that's just a feature of a particular protocol, or, in fact, a specific signal transmission scheme. There's Princeton, I think. Yes, Princeton. But as for thank you, it wasn't you who figured it out. Well, then it must have been someone else, right? Accordingly, the peculiarity of this particular data transmission format is that it transmits a 0 at the beginning and a 0 at the end. So in this case, we moved away from the physical representation of the signal, converted it into a logical one, and using some additional formulas, yes, very intimidating ones, and honestly, it would take a long time to explain, and it's not very interesting. So we converted it into this form, and basically we get the same result. But this scheme works much faster. I don't know, someone's messing around. All right, we press the button again. Well, that's right, yes. When you need to ring, you don't ring. Maybe you died? Well, something apparently went wrong. It seemed like everything was working, but the point basically remains the same. So, let me open the very last slide for you now. So, today we have, I sincerely hope you've learned something extra, something new, and perhaps studied something interesting as well. And I really hope that you actually found the talk to be interesting and engaging. And of course, please do subscribe to all our social media channels and stay connected with us. I currently work at the company Bastion, where I am specifically responsible for the hardware hacking division, for hardware and software hardware hacking. And in fact, we not only carry out similar types of attacks, but also, just like my colleagues, the previous speakers, we extract firmware and so on. This is the website of the company Bastion, where we work. This is my personal project, and yes, I'd also like to ask you to subscribe to our Telegram, as well as to our Bastion Work Telegram chat. That's basically all I have. I'm ready to answer your questions. We have 6 minutes left.
Could you tell me, you showed the GNU radio application and it seems a bit more complicated than the previous one. How do you figure it out? Maybe you could recommend some literature on it.
The application is open source, also written by Michael Osman, who developed HackerAF. He has a number of courses on YouTube. I won't go into further details about that, yeah? But again, all of this is easy to Google. It's all easy to learn. The only thing is, unfortunately, I didn't mention this at the very beginning of my talk. Hardware hacking in the Russian Federation is currently very underdeveloped for the simple reason that there is practically no literature on this subject in Russian. Everything that is studied, everything that is developed, it's all in English. So if you want to really dive deep into this, I recommend, if you don't already know English, and if you do, that's great, just learn English. And basically look for information not in Russian, because it's either limited or, frankly, might be incorrectly translated. So learn English and basically study all of this using foreign resources. Well, Michael Osman has a beginner's course on GNU Radio Companion. But in general, honestly, if you just Google it or use Yandex, if we're talking about import substitution, you can easily find and study all of this. I won't argue. It will be a bit painful, a bit difficult. You need an understanding of physics, an understanding of how all of this works. But once you master it, I think you'll be one of the most sought-after professionals in this field.
Thank you.
Ivan, hello. I wanted to thank you for such a great presentation. I have two questions in mind. On the first slide, or one of the first, you compared different types of boards. If we don't take price into account, which one would be the most convenient for a beginner to use and doesn't require extensive knowledge? Basically something you can take out of the box and start using right away.
But you'll need some knowledge in any case. There's no way around it. If we're talking about a balance between price and quality, I would recommend starting with the RTL SDR. Let me show you what it looks like. Here it is, the original one. Its price on eBay is around $40, but I think on AliExpress you can get it for about 5,000 rubles. It receives very well, the signal is very clean. Sometimes with the Hack RF I run into the problem that the signal is dirty because the frequency range is large and the antennas aren't always suitable, right? But usually what do? We just plug in some antenna, more or less, that receives this or that, and that's enough. In this case, the RTL SDR receives a very clean signal. It lays everything out perfectly. You can be at a considerable distance from it and still work with it just fine. The only thing is, I want to emphasize, the RTL SDR does not transmit data back into the air. So to get started, to understand how it works, to analyze those same signals, for example, I used to buy remote-controlled cars. They cost about 500 rubles. Buy the cheapest one you can find, preferably operating at 27 megahertz. Don't buy cars that run on 2.4 gigahertz. That signal, well, it's not suitable for beginners. Get a remote-controlled car or a little helicopter, it doesn't matter. The main thing is that the data transmission frequency should be 27 megahertz. Buy an RTL SDR, maybe even, I'm sure someone is selling them on Avito, well, in our...
On AliExpress, they cost about 3,000 on average.
There you go, all the more reason. And basically for 3,000 or 4,000 rubles, you can put it all together because it already comes with antennas, stands, suction cups for the window. So the signal is received better. And in general, for about 5,000 rubles, we can do this. By the way, yes, that's a good question. I think it, honestly, I don't remember anymore. No, it works from 24. So basically, you can also listen to CB radios, but that's the civilian band where the truckers are. And basically, you can listen to the radio. You can even intercept a bit of GSM, but obviously you won't be able to actually listen in because everything is encrypted there and so on. But again, yes, you can catch satellites. You can listen to conversations between air traffic controllers and pilots. And basically, everything that falls within this frequency range. If you find an Abico 25 modulator demodulator, you can also listen to some organs.
Thank you. I have another question. In this table, it says that the 433 megahertz module for Arduino has a transmission function. So in fact, we could carry out the same kind of attack as the one you demonstrated. Is that correct?
Yes. In this case, we have a transmitter. We see here a generator, a wave generator, and essentially a receiver. You can buy them separately, but they're usually always sold as a pair for about 200 or 300 rubles, I think. If you already have some Arduino kit, printed circuit boards, or a Raspberry Pi, then you can easily plug it in. There's plenty of information online about how to make pretty decent things out of this stuff. Plus, there are also enthusiasts who use these devices to create a kind of universal scanner. Again, they do this using a Raspberry Pi, get in a car, and start driving around the neighborhood. And wherever someone is transmitting or receiving something, it's immediately decrypted, recorded, and so on. But you shouldn't do that. It's not advisable.
Thank you very much for answering the questions.
Yes.
Thank you. Could you tell us where to start when studying rolling codes? I mean, not something too complicated or encrypted, but also not just a simple increment, maybe some standards or protocols.
Well, with rolling codes, the hardest part is understanding the algorithm.
Exactly, to really understand it.
How it's generated, yes. Usually the simplest and quickest thing I start analyzing is whether it's tied to the date and time. If we're talking about Linux devices, for example, the same timestamp, right, which converts seconds, minutes, and the date, the year, into a normal, well, not a hash, but rather how many seconds have passed since January 1st, 1970. Yes, it's millions, even billions, and usually they take this code and add some kind of their own payload, a salt, and then transmit it. So when you're recording the signal, try to, well, of course, record the time at which you're transmitting and also convert it into the Linux timestamp format. But again, I want to point out that in this case, there must be synchronization between the transmitter and the receiver in terms of time.
Uh-huh.
If that's not the case, then this option is ruled out and you'll have to look for other solutions. You'll need to take it apart and extract the firmware using, for example, SC441 programmers. So basically, Alexander knows, he was with us for 2 days. We had our booth set up and we were demonstrating exactly how this can be done. You take apart the device, just like I did with the lock. You connect either with a clip, a logic analyzer, or an oscilloscope, depending on the situation. And you observe live what's going on inside as you take it apart. If that doesn't work, then it's just logic and math. You have to try to work through it all somehow. So in this case, hardware hacking skills specifically for extracting firmware are really essential.
Got it. In a simple case, the authenticator is just time. Thank you. The authenticator is time. There.
Well, in the simplest scenario, yes, it can be like that. But again, take a closer look. See, the battery is inserted here and here, right? So, you know.
Thank you.
Hello. Thank you very much for the presentation. I have a question. Geolocation is a big problem in Moscow these days. And in the case of jammers, I guess there's nothing you can do. But if...
You can actually make a jammer, including through a hacker.
No, it's hardly possible to receive a signal if someone has turned on a jammer. But if someone is spoofing the signal, then most likely you can filter out the strong signal from the ground and still receive the signal from the satellite. My question is, what non-obvious pitfalls might arise along the way?
So I'm being told here that time is up. Let me try to answer quickly in a minute. At the beginning, we discussed what interference is. And accordingly, if the signal from the ground is stronger, more powerful than, let's say, the white noise generators that transmit and jam the signal at the GPS frequency, then in this case, you will get, if it turns out that you are transmitting in one room and right next door in the neighboring room someone is jamming, well, then it's a matter of, well, as they say, you'll have to compete. Whoever has the stronger signal wins. Guys, I apologize. Time's up. Yes, thank you very much for your questions. Time is up. If anyone has additional questions, yes, after the presentations, in 5 or 10 minutes, I'll pack up the equipment. If you're interested, yes, I'm ready to answer questions. Our organizers have arranged a kind of contest, yes, for the best question. I'd like to give it to the young man. Yes, thank you very much. Great questions, and please keep learning.
Thank you, Ivan.